Log on, tune in, find out. Another good idea from Cambridge.
Important information about participants over there. Please take notice. And second speaker today, we have Dominic Joyce from Oxford to talk about D-manifolds, a new theory of derived differential geometry.
Thank you. So this talk has got some derived things in it, and it's got two categories, and there's going to be moduli spaces. So I suppose it does fit in this program, but even so, it's fairly far out from the what's usual, I suppose. So basically, I'm trying to invent a new kind of space, which I call D-manifolds, which is going to be the natural structure you want to put on various kinds of interesting moduli problem. So if you're interested in this, well, the slides are available on my webpage, but also there is some chapters from a book I'm writing. Also, you can download from there. And the kind of technical chapters on D-manifolds without boundary are basically complete, and you can read them there. And I'm still working on the things with corners aspects of things. Okay, so just to start where everybody knows.
Could you, Dominic?
Yeah.
Could you put your used slides on the other?
Yep.
It's not so much this one as the next one.
Okay. So yeah. Okay. So lots of important areas in both differential and algebraic geometry involve moduli spaces of some geometric objects, and then you count the points in your moduli space to get invariant with interesting properties. So I cut my teeth in Oxford in the 1980s, so I know that the thing you do with a moduli space is you count it and you make an invariant like Donaldson invariance. So examples would be Donaldson invariance, Seiberg-Witten invariance, Gromov-Witten, Donaldson-Thomas invariance. That's really moving from differential geometry, Donaldson and Seiberg-Witten, to algebraic geometry and Donaldson-Thomas and Gromov-Witten, which has a symplectic version with almost complex structures, or an algebraic version counting curves. So more generally, if you think about your invariant as being something like a vector space or a category, then you can fit Floer homology theories, contact homology, symplectic field theory, and Buchaya categories. All of these are mostly parts of symplectic geometry, also fit into this framework of building some invariant by counting points in some moduli space. So you can draw out some common features of these invariance theories. So you start with some geometrical space X that you want to study. For example, a compact oriented four manifold. And then you define a moduli space M of some auxiliary geometric objects. For example, you might choose a Riemannian metric on your four manifold and then study the moduli spaces of self-dual connections on some vector bundle. So this moduli space M is initially a topological space. Hopefully it's compact in Hausdorff, but in general it's not a manifold. It could have some quite bad singularities, but you still somehow manage to treat it as if it is a compact and oriented manifold of some known dimension k. If, for instance, this is a moduli space of solutions of some nonlinear elliptic partial differential equation, then k is the expected dimension of the moduli space, namely the index of the linearization of the operator. So somewhere or other you define a virtual class, M virtual, which may lie in the homology group of M over the integers or the rationals, or it may perhaps lie in some other homology group of some other space which M maps down to. And this, in some sense, counts the points in M. And the important thing is that this virtual class is essentially some kind of topological invariant. It's independent of choices in the construction, such as the choice of a metric on your four manifold to define an innocent moduli space with, or if you're doing Gromov-Witten theory, then this class would be independent of the choice of almost complex structure you chose to define your moduli space of homomorphic curves. Okay, so, and there's interesting information contained in this virtual class. So, methods for defining virtual classes vary, particularly as the divide between the differential geometry side of things and the algebraic geometry side of things. In some nice, particularly in the differential geometry cases, sometimes you can arrange for your moduli space n to be a smooth manifold. For instance, in cyber-Witten theory, with numeric choice of metric, you'll get smooth moduli spaces. But if you can't make it smooth, if the parameters you can deform are not enough to smooth the moduli space, then you have to take another approach, which is that you give your moduli space some extra geometric structure, Cody G, let's say, and we use this extra geometric structure to define the virtual class. So in algebraic geometry, things are fairly much sorted. Usually one would say M is a scheme, or perhaps a Deligne-Mumford stack, with a perfect obstruction theory, and then you can use that to define a virtual class in general homology, and off you go. So in symplectic geometry in particular, things are much more of a mess. So there are reasons why you can, if you're looking at moduli spaces of J-homomorphic curves, you can't make them smooth, however hard you try, because if you're looking at J-homomorphic curves, then you can have curves which are multiple covers or branch covers of some other curves, and you can then prove that at a branch cover, even if you make your almost complex structure generic, you'll get non-smoothness, and in fact, in some sense, you can have things where the singular strata has to have larger dimension than the overall moduli space, and so on. So in symplectic geometry, at least, you can't get away from having singular moduli spaces. So there are two main competing geometric structures. There's Kuranishi spaces, which occur in the work of Buchaya, O, Ota, and Ono from symplectic Gromov-Witten theory in the 1990s, and then Lagrangian Floer cohomology. And then also there's the polyfold group around Hofer, Wysotsky, and Zander, and they're concentrating more on symplectic field theory. But these are both geometric structures you can put on moduli space of J-homomorphic curves, which are really differential geometric moduli spaces. Sorry?
Holomorphic equation, that's what they did originally, right?
Yeah.
That does get you to the smooth.
Is that... You might have problems with the orbifolds.
Yeah.
So, yeah, the problems are around the orbifold points in particular. Okay, so what I'm talking about, I call D-manifolds and D-orbifolds. So these are kind of derived smooth manifolds in the sense of derived algebraic geometry. So let me tell you some properties of these. Firstly, they form a strict two-category, D-man. So we have objects X, which are your D-manifolds, one morphisms, F and G going from X into Y, which are basically derived versions of smooth maps. And also, kind of non-classically, you have two morphisms, which I'll write as eta, going between two one morphisms F and G of the same space. Secondly, smooth manifolds embed into D-manifolds as a full subcategory or two subcategory. Thirdly, you can do all of this with boundary or with corners, and we can also do all of this for orbifolds. So we have D-manifolds with boundary, D-manifolds with corners, D-orbifolds and with boundary and with corners. You wouldn't believe how much trouble sorting out the issues involved with corners has been. But the corners versions of the theories are important in symplectic geometry, particularly for things like Lagrangian Floer cohomology. There you have to look at moduli spaces of J-homomorphic curves with boundary upon a Lagrangian. And these moduli spaces, they're kind of modelled not on manifolds without boundary, but on manifolds with boundary and with corners. Because a family of J-homomorphic curves can develop a boundary node, and that's something which happens in real codimension 1. So for these things, you don't work with virtual classes in homology. You really have to work with virtual cycles or virtual chains in the chains of some homology group. And if you looked into FO cubed, you'll find that the problems with forming virtual chains associated to these singular moduli spaces with corners have to be seen to be believed, really. So really where I was coming from was trying to find a way of straightening all of these things out. Okay, so lots of differential geometry extends very nicely to D-manifolds. For example, submersions, immersions, orientations, submanifolds, fiber products, transverse fiber products, cotangent bundles, and so on. And these D-manifolds are really very nicely behaved as a two-category and as a kind of two-category of geometric spaces. You can write down a kind of shopping list of all of the nice things you would hope would happen for some kind of category of derived manifolds. And basically on my shopping list at least, all of the boxes are ticked. Next, and linking back to moduli spaces, basically almost any moduli space used in any enumerative invariant problem over the reals or the complex numbers should have a D-manifold or a D-orbifold structure, which will be natural up to equivalence. So there should be truncation functors. So this bit is really work in progress because I haven't written that up yet. But there should be truncation functors going from two D-manifolds and D-orbifolds from the kind of things which people generally use, such as C-schemes with instruction theories, Konishi spaces, polyfolds with Fredholm perfections, and so on. So the proofs which people have already given that the various moduli spaces people are interested in have appropriate geometric structures will then immediately imply that you also have a D-manifold or D-orbifold structure. And finally, you can make virtual classes, virtual cycles, virtual chains in the boundary or corners cases for compact and oriented D-manifolds and D-orbifolds. So that tells you that this geometric structure, D-manifolds and D-orbifolds, contains the information which you wanted if what you wanted to do was to build some kind of invariant theory like Donaldson theory or Lagrangian Floer cohomology or whatever. So D-manifolds and D-orbifolds, they provide a unified framework for studying enumerative invariants and exotic homology theories, the homology theories, Lagrangian Floer cohomology, Fukaya categories, and so on. So they've also got other applications. I have in mind possibly string topology, things of that kind. And well, I at least think that they're interesting and beautiful in their own right. So this is not a completely new idea. D-manifolds and D-orbifolds are related to various other classes of spaces already studied. In particular, the Konishi spaces of Fukaya, Ota, and Ono in symplectic geometry, and to the derived manifolds of David Spivak, who's a student of Jacob Lurie, and that's really an offshoot of Jacob Lurie's derived algebraic geometry program. Okay, so let me first talk about Konishi spaces. Konishi spaces were defined by Fukaya and Ono in 1999 in their topology paper on Gromov-Witten invariants and symplectic manifolds, and then further in Fukaya, O, and Oto, and Ono in 2009, the great big book, or two books, on Lagrangian Floer cohomology. So this is the geometric structure they want to put on moduli spaces of J homomorphic curves in symplectic geometry, where J is some almost complex structure on a symplectic manifold, and you're also interested in homomorphic curves with boundary and some Lagrangian. So the basic idea is that a Konishi space is locally modelled on the zeros, S inverse of 0, of a smooth section S of a vector bundle E over some orbifold V. So there are quite a lot of problems in this theory in the foundations, and it's, in my view at least, basically incomplete. And I don't want to to diss with higher and so on too much. And basically they pushed the theory as far as they needed to do the job they wanted to do. But for instance, what Konishi spaces are as geometric spaces is really not made very clear. And there's not even a notion of morphism between Konishi spaces. All they tell you is what is a morphism from a Konishi space to a manifold. And there's no good notion of when two Konishi spaces are the same, for instance. And with hindsight, I think you can see that the reason that they weren't able to develop that is that to do the job properly requires ideas from derived algebraic geometry, which weren't really available at the time, or perhaps weren't current in the symplectic geometry community. So my starting point for this project was that I was trying to find the right definition of Konishi space. So I claim that the answer to this is that a Konishi space is, or rather should have been defined to be, a D-orbifold with corners. And that this is the right structure to put on moduli spaces of J-homomorphic curves. Okay, so much more recently.
Excuse me, what's the relation between M and V?
Sorry?
What's the relation between
M and V? M is S inverse of 0. So basically, your moduli space looks like the zeros of finitely many functions on a manifold. Or in the orbifold sense, it's the zeros of some smooth section of a vector bundle. So you get this in deformation theory, either in the algebraic or the differential geometric context. You start with some point in your moduli space, and then you get a Konishi model, which says that locally your manifold looks like the zeros of a smooth map from the deformation space to the obstruction space. And E is the obstruction bundle, V is really the deformation space. But the real problems in the theory come when you try to glue together two different neighborhoods of this kind. So what's the right notion of transition function between two neighborhoods of that thing was the thing which bedevils the theory of Konishi spaces. Okay, next let's talk about derived manifolds. So these were defined by David Spivak as a paper in the Duke Mathematical Journal, volume 153. He's a student of Jacob Lurie. So a lot of my ideas are really taken from Spivak. So the difference between D-manifolds and his derived manifolds are that D-manifolds are much simpler. So this is the first time I've talked about this to an audience that will probably understand what I've got to say. So I'm very interested in feedback from you guys. And I live in fear that someone will point out some killer problem with this theory, which we now have to throw it all away. Because basically, if what I'm saying is right, then somehow the derived algebraic geometry people have been, in some ways, wasting their time all these years. I don't. So how I got here is that, well, I tried to understand derived manifolds, and basically I was too stupid to do so. And derived manifolds form an infinity category, or a simplicial category, and I couldn't get any kind of differential geometric intuition for what the higher morphisms meant. So the definition uses some quite advanced and scary technology like homotopy sheaves and Boostfeld localization and things like that. So if you're Jacob Lurie or Ingranowski, then these things are trivial. But if you're somebody like me, when you hear terms like this, you should run away. But the construction I'm going to talk about basically involves Hartshorne algebraic geometry style algebraic geometry, and kind of almost nothing more than that, except for the fact that I'm working in a C-infinity world with kind of smooth functions rather than algebraic geometry, so there's a whole kind of C-infinity rings things coming in. But basically, the derived algebraic geometry stuff is built using schemes and coherent sheaves and almost nothing more than that. So D-manifolds, I think, are a two-category truncation of derived manifolds. And I claim that this truncation remembers all of the geometric information which you need to know if you're a real person like a symplectic geometer. In particular, it retains all of the geometric information you need to form things like virtual cycles and do counting invariants or Lagrangian Floer cohomology and so on. So let's talk about, okay, if we're trying to build some putative category of derived manifolds, let's talk about why it should be a two-category. So there's two things to justify. One is that why should it be at least a two-category, and the other is why should it be at most a two-category. So one reason why it has to be some kind of higher category is this. So one property I want of derived manifolds is that it should contain manifolds as a subcategory. So these things are generalizations of manifolds. And if x and y and z are manifolds, and you have smooth maps, G going from x into z, H going from y into z, just smooth maps of manifolds in the usual sense, then there should exist a fiber product, W, which is x cross over z of y. This fiber product should exist in derived manifolds. So if you're not happy with fiber products, think about x and y as being submanifolds of z, and we're now talking about taking an intersection of submanifolds. Okay, so if the submanifolds intersect transversely, then their intersection is a submanifold in the usual sense. But if the submanifolds are somehow kind of tangent to each other, intersecting non-transversely, then the intersection might be some horrible subset, you know, a fractal or something. And you can actually get very weird subsets as intersections of submanifolds, and but nonetheless we want this to be in some sense a derived submanifold. And you should have virtual dimension, which dimension of x plus dimension of y minus dimension of z. So that's certainly the dimension you'd expect for the transverse intersection of submanifolds, if you like. But we don't require G and H to be transverse, and we allow the virtual dimension to be negative. Okay, so let's consider almost the simplest case we can, when x and y are a point, which I write as star, and z is the real numbers, and G and H are taking the point to 0. So 0 is, I'm intersecting the point 0 with itself as submanifolds of the real line. Okay, so if the derived manifolds were an ordinary category, then because the point is a terminal object, there is a unique fiber product star cross R star, which is the point star. So in that case, basically, just by it being a category, rather than a higher category, you get an intersection which is well defined, but it has virtual dimension 0, not -1, which is what you're expecting. So that tells you that derived manifolds must be some kind of higher category, because otherwise the fiber products could not have the universal property we want and give us derived intersections with the right virtual dimension. Okay, so that's why derived manifolds have to be at least a two-category. So perhaps more non-trivially, why should it be at most a two-category? So two approximations you can think about for derived manifolds are C-scheme X with a perfect obstruction theory, or a DG scheme, which is some quasi-smooth, if I got the right form for that. So in both of these cases, you've got a cotangent complex in the derived category of coherent sheaves on X, which is concentrated in 2 degrees, -1, 0. So locally, you can write it as a morphism between 2 vector bundles. So a vector bundle E-1 into E0, after equivalence. It seems reasonable I claim at least that you should be able to capture the behaviour of such complexes in a 2 category, because there's 2 degrees going on here. Now, in general, for your quasi-smooth DG schemes, the cotangent complex is concentrated into 2 degrees, but the structure sheaf is concentrated in lots of degrees. It can have arbitrarily many non-zero, cohomology and arbitrarily many degrees, and therefore, in the usual sense, quasi-smooth DG schemes are a higher category, not just a 2 category. But I'm claiming that this truncation idea somehow sorts all that out, but I don't really know how yet. Okay. So now let's talk about how we define these. So algebraic geometry, which is based on algebra and polynomials, has excellent tools for studying singular spaces, namely the theory of schemes. On the other hand, ordinary differential geometry, which is based on smooth real functions and calculus, this is very good at dealing with non-singular spaces, namely manifolds, but on the whole it deals poorly with singular spaces. So we're looking for some kind of category of differential geometric objects, including manifolds and including some classes of singular spaces. Now, there is a not very well known theory of schemes in differential geometry, which are called C-infinity schemes, and this goes back to authors such as Lovert, Dubuc, Mergic and Reyes in synthetic differential geometry in the 1960s and 1980s. So that's what we're going to use. Now, what the synthetic differential geometers were trying to do is that back in the 19th century, people like Lie were writing differential geometric proofs using infinitesimals. Okay, so, but of course the proofs kind of weren't valid because differential infinitesimals on the face it didn't make any sense. So what the synthetic differential geometers wanted to do is to show that those methods of reasoning, proof using infinitesimals, is valid. And to do that, what they wanted to do is to find a category of geometric objects which included manifolds, and it also included certain other objects such as a double point, kind of infinitesimal things, and had some kind of universal properties which would relate the two. And the C-infinity schemes fit that, ticked all those boxes. But as far as they were concerned, once they found a category which modelled the reasoning of synthetic differential geometry, the job was done, and they could go home for tea. So basically, having proved that infinitesimal reasoning methods in differential geometry are valid, they just didn't take this idea any further. But it was taken up again by David Spivak in his derived manifolds, and I'm doing the same thing in mine. So let me tell you about C-infinity schemes. So the basic idea is that of a C-infinity ring. So let's start with some manifold X and consider the set C-infinity of X, a set of smooth functions, C going from X into the real numbers. So in an obvious way, this is an algebra of the reals, because you can add functions, you can multiply smooth functions, you can multiply them by a real constant. But there are actually many more operations on C-infinity of X than that. For instance, you can exponentiate functions. If C going from X into R is smooth, then X of C going from X into R is also smooth. So therefore, this gives you an operation, exponential, going from C-infinity of X into C-infinity of X. This is algebraically independent of addition and multiplication. Of course, you can write a power series converging, getting X as a limit of polynomials in C, but that's not really what we're about. We're trying to think about these things in strictly algebraic terms. So a way of encapsulating all of the interesting algebraic operations on these things is this. if you consider f going from r to the n into r to be a smooth function, you then define an operation, big phi f, going from n copies of the smooth functions on x into the smooth functions on f, x by phi f of functions c1 up to cn. It's just f of c1 up to f of cn for all points little x and big X. So that's a large class of operations on C infinity of x. It includes addition, because you can get it from the map f r squared into r, taking c1, c2 to c1 plus 2. Multiplication comes from c1, c2 goes to c1 times c2. So this is the basis of the idea of a C infinity ring. So a C infinity ring is a set that you see together with operations phi f going from c to the n into c for all smooth maps f going from r to the n into r for n non-negative, satisfying some fairly obvious conditions. Well, one is kind of composition of functions. If you've got you have a bunch of functions and you can compose them, then you have a natural identity on these operations phi f, and the other is that projections to one coordinate from c to the n should be the obvious thing. So this is trying to encapsulate all of the algebraic structure which you naturally find on the smooth functions on a manifold into one great big structure satisfying a whole load of identities. So the natural notion of morphism of C infinity rings is a map phi going from C into D, which commutes with all of the operations phi f for all smooth functions f. So this gives you a good category of C infinity rings, which we write like that. Okay. So then for any manifold x, the smooth function C infinity x on x is a C infinity ring, and you can recover the manifold x from this up to isomorphism. Basically, the points of x are in one-to-one correspondence with algebra morphisms from C infinity of x into R, and then you can put the topology on that and recover the smooth functions and so on. So if you have a smooth map f going from x into y of manifolds, then the pullback function going from C into y and C infinity of x is a morphism of C infinity rings. So therefore you get a functor from manifolds to the opposite category of C infinity rings, taking x to the smooth functions on x and f going to pullback of smooth functions. And this is full and faithful, meaning that the one-to-one correspondence between smooth maps from x into y and C infinity ring morphisms f star from C infinity y to C infinity of x. So you can think about manifolds as examples of C infinity rings, and you can think about C infinity rings as being generalizations of manifolds. But then if you think about C infinity rings as giving you a new class of smooth spaces, you'll see that this class is really huge. There are far more C infinity rings than there are manifolds. So for instance, for any topological space x, C0 of x is a C infinity ring. So spec of it is a C infinity scheme. So this new class of geometric objects we introduce is really huge. Okay. So let's now talk about C infinity schemes. We can develop the whole machinery of scheme theory in algebraic geometry, but replacing rings or algebras by C infinity rings throughout. So there's a good paper by this by Dubuck in the American Journal of Mathematics. There's a paper by me on the archive. So basically the synthetic differential geometry people didn't develop the ideas very far. So this is a paper by me which takes machinery a bit further, far enough to do what I want to do with D-manifolds. So we obtain a category, C infinity schemes, of C infinity schemes x, OX, where a C-infinity scheme is a topological space X and a sheaf of C-infinity rings, OX and X, which is locally modelled on the spectrum of a C-infinity ring. So the appropriate notion of spectrum here, in algebraic geometry, the points are prime ideals. Or you could perhaps consider maximal ideals if you're working over some nice field. For C-infinity rings, the points are ideals, maximal ideals whose quotient field is R. So the most restricted notion of points. So we don't have points corresponding to subschemes and submanifolds and so on. That's because I want the spectrum function, if you start with a manifold, the smooth function of a manifold, I want the spectrum function to give you back that manifold. You don't want a kind of penumbra of kind of schemy points as well.
Is spec of C0x X?
I think so. I thought about that, but yeah, I guess so. Well, if X is nice enough, anyway. Yeah, you might have to worry if it's, you certainly need some kind of Hausdorffness conditions, I would think. Okay, so we now get a full and faithful embedding from manifolds into C-infinity schemes. So that is, this notion of C-infinity schemes captures your notion of smooth map between manifolds correctly. Okay, so you can define vector bundles and coherent sheaves and quasi-coherent sheaves and the cotangent sheaf T star of X on this. So and this becomes an abelian category. Quasi-coherent sheaves. So some differences with conventional algebraic geometries. Well, so two pieces of good news. Firstly, affine C-infinity schemes are Hausdorff. So in ordinary algebraic geometry, you have problems because the Zariski topology is rather coarse, and so you tend to have to use the étale topology to do things. But in the C-infinity world, that's not necessary. Secondly, partitions of unity exist subordinate to any open cover on a sufficiently nice C-infinity scheme X, where nice really means Hausdorff, paracompact, and locally finite dimensional. So you're able to join together local choices of data very easily. And this is good for gluing things, because quite often in differential geometric moduli space problems, your moduli space is presented really in terms of a small open neighborhood with some structure, and then a nearby open neighborhood with another structure, and some kind of transition functions. So you're always having to glue things together on small neighborhoods. And partitions of unity exist in this world which enable you to do that. A piece of bad news is that C-infinity rings, such as the smooth functions in RCN, are not Noetherian as our algebras. So basically, this is we're looking at some kind of non-Noetherian schemes, which causes problems of various kinds. One problem is with the notion of what's the right notion of coherent sheaves. My notion is locally finite presented, and this notion is not closed under kernels, and so therefore it's not an abelian category. But that's why I tend to use quasi-coherent sheaves in Okay, so now let's tell you how to build a D-space, to know what C-infinity schemes are. So I'm going to define D-manifolds as a two-subcategory of a larger two-category of D-spaces. So my D-spaces are just derived versions of C-infinity schemes. So C-infinity schemes are things which have kind of got tangent spaces, or cotangent sheaves, whereas D-spaces are things which have got cotangent sheaves and obstruction sheaves, essentially. They're a kind of two-category version. So a D-space is got 5 pieces of data in it. There's a C-infinity scheme X. There's another sheaf OX primed of C-infinity rings on X. There's a quasi-coherent sheaf EX on X, and well, it might be easy just to look at this exact sequence. So there's an exact sequence happening on topological space X, OX and OX primed are both sheaves of C infinity rings. IX is a morphism of sheaves of C infinity rings. So basically, this tells you that X is a C infinity scheme in two ways. And this is a morphism between those two schemes, which is the identity on points. Then we've got a quasi-coherent sheaf, which is the kernel here, which is therefore surjecting onto the ideal in here, which is the kernel of that morphism. And so the kernel of this morphism, going from OX prime to OX, is a square zero ideal, or a sheaf of square zero ideals, which means that these ideals are OX modules rather than just OX prime modules. And then we have a surjective morphism of OX modules, or quasi-coherent sheaves on X, from EX to the ideal there. So this slide and the next slide are the kind of technical part of the talk. So I'm sorry if this is going to be a bit confusing. So square zero ideals, square zero extensions of schemes seem to pop up here. I don't really understand why, but it's the key to getting this two-category truncation right.
This is like the truncated cotangent complex or something in algebraic geometry.
Very likely, yes.
So more really like this O prime, you think, as being the smooth space that lies, and this map here are the equations that cut it out. The J is the equations that cut it out. Cut out your virtual structure.
Well, so let's suppose that this is the sections of some smooth section of a vector bundle. Then OX you should think of as being as just the zeros of the sections as a subscheme.
The bad thing.
Sorry?
The singular.
The bad thing.
Yes, OX is bad. Well, they're all bad. But OX is the zeros of the sections. OX primed is the zeros of the square of the section. So it's kind of largest square zero extension in the smooth thing. And then EX into OX. So EX is the sections of the obstruction bundle, or the dual of the obstruction bundle, divided by the sections times the section equals 0. And then JX is the map from the it's basically multiplication by the section. Sorry, yeah. Okay, so we're trying to build a two-category. So next we need a notion of one morphism. So this is a triple of F, F primed, F double primed. So F is a morphism of the underlying C infinity schemes in the most obvious way. So if F, so that consists of a continuous map F of the topological spaces together with F sharp is a morphism of sheaves of C infinity rings. And then the other pieces of data fit into this commutative diagram. So we've got these exact sequences here, lift up to a diagram of sheaves of C infinity rings or their representations on X, and so that comes from the morphism of from the C infinity scheme morphism. We have to be able to extend it using two maps F primed and F double primed here.
How should we think of smoothness in this game? Like, how can you tell from the sheaf of rings when its spec is going to be smooth in the usual sense?
Well, if the e's are 0, that's a good start. Well, so if the e's are being obstruction bundles, so well, if the obstruction bundles are 0, then in this world at least, that means it's a classical C infinity scheme, not a derived object. In the D-manifolds world, then the e's are 0 tells you it's a manifold. Okay, so because I'm making two categories, we also need a notion of two morphisms. So the two morphisms are basically a kind of morphism going from there to there in this diagram. So if we got an F and one morphism F and G, then the underlying C infinity scheme morphisms have to be the same, which means that these morphisms are the same, and we want some kind of a morphism going that way. But in fact, for weird reasons, I make this morphism factor through the cotangent sheaf of this thing. So the two morphisms are morphisms from the cotangent sheaf of the O-primed thing on Y, tensored with OX to here. So this is a morphism of quasi-coherent sheaves on X. And then you get the kind of things you expect, which is that the G primed and G double primed are built from the F primed, the F double primed by something linear in this two morphism eta. So this is doing some kind of it's basically some kind of a two morphism of complexes of length 2. Okay, so the theorem is that this defines a strict two-category, D spaces, and all fibre products exist in D spaces. There's some explicit construction you can use to build fibre products.
Dominic, I've missed something basic. I mean, you said there were a lot more C infinity rings than there were manifolds.
Yeah.
How have you got rid of those? Somewhere in this.
They're still here. So D spaces is huge. So I'm about to define a two subcategory, D-manifolds, which is much smaller. Okay, so we can map C infinity schemes into D spaces by taking a C infinity scheme X. So the OX primed is just OX. The E, the obstruction sheaf, is 0. The I is just the identity morphism, and the J is 0. So we're just talking about the exact sequence is 0 into OX into 0 in the obvious way. So this embeds C infinity schemes, and therefore manifolds, as discrete two subcategories of D spaces. So for transverse fibre products of manifolds, the fibre products in manifolds and D spaces agree, but non-transverse fibre products are different. So as I said, the use of square zero extensions to define D spaces seems to be the key to defining a good two-category, and in some kind of nicely truncating Spivak's infinity category. But I really don't know why it is this works, and if somebody knows, you're welcome to tell me. Okay, so yeah.
We need to work with sheaves and not with their global sections.
Sorry? Oh, sheaves rather than global sections. Well, to be honest, we probably could work with affine things, and therefore we could just work with infinity rings and with global sections. The reason I didn't is that for some things like gluing things over patches, it's not so easy to make sure that you start with some affine things, so you end up with an affine thing. But probably most interesting things are affine. So in conventional algebraic geometry, there are very basic things like projective space, which are not affine. In C infinity world, because basically almost every interesting C infinity ring C infinity scheme is an affine C infinity scheme. So we could just work with things and their representations rather than with schemes. Anyway, so inside these spaces I want to define a two subcategory of D-manifolds. So I define a D space to be a D-manifold of dimension n, which is an integer, it's allowed to be negatives. If you can cover X by open subspaces Y, which are equivalent in D spaces to a fibre product of the form U cross V over W, where U and V and W are manifolds without boundary, and dimension of U plus dimension of V minus dimension of W is n.
Can you tell us what equivalent was?
In the two-category sense, so two objects in two-category equivalent if you've got a morphism going one way, morphism going the other way, and so G of F is too isomorphic to the identity on X, F of G is too isomorphic to the identity on Y.
So if I cut the origin out of R by the equation X,
Yeah.
is that equivalent to just the origin on its own?
I mean, so X equals 0? Yes. Yeah, so X equals 0 in R is equivalent to the point.
Why?
X squared equals 0 is a double point, it's not equivalent.
But why are they
Why are they equivalent?
Depends how you form the fibre product. Well, in the sense that they just are. You can form a diagram and check that it's two Cartesian. It's got a universal property. But so one way is to check a two Cartesian property. The other is that there's some explicit way to define the fibre product. So if you did a kind of, so you're talking about point cross R over R. If you build that as a D space, you'll find it's got, well, one way of doing it is you find it's a struction bundle R and the kind of tangent space R, and then a kind of identity map going between them. And then there's morphisms going both ways with the point, and there's a kind of important two morphism which maps the R to the R as an identity. I don't know. I'll write it down for you later.
You're not dividing out by homotopies or quasi-isomorphisms?
No, absolutely not. So and if you want to form a derived category, then you have to localize by some category of somethings. You want to invert quasi-isomorphisms or something like that. Here, I'm absolutely not doing that. I'm telling you exactly what one morphisms are, exactly what two morphisms are. There's no localization.
Is this bigger than had we just taken manifolds and then thrown in all the fiber products of manifolds? I mean, this is like locally fiber products. Could you have just thrown in the global ones, make it closed under fiber products, and say you're done?
In fact, it turns out not to be bigger. Okay, so I can show that every compact D-manifold is globally a fiber product.
Okay.
And so the way you do that is you embed it into R to the n, and then you show that it's locally equivalent to the zeros of a section of a vector bundle over an open neighborhood of the image in R to the n. But that's a kind of non-trivial theorem. And as far as I know, the converse, the corresponding result may well not be true in the orbifold case. Okay, so we think about a D-manifold as being a classical C-infinity scheme, which behaves like a kind of one-category object, together with some derived data, OX, EX, IX, JX, which are affected by two morphisms, and they're kind of higher categorical stuff. So we write D-man for the full two subcategory of D-manifolds and D-spaces. So it's not closed under fiber products, but you can say that all fiber products of the form X cross Y over Z, where X and Y are D-manifolds and Z is a manifold, these exist in the two category of D-manifolds. More generally, there's some notion of D-transverse fiber products. So to be a transverse, so for an ordinary transverse fiber product in manifolds, basically the tangent bundles of X and Y need to surject onto the tangent bundle of Z. In the D-manifolds, the obstruction bundles of X and Y have to surject onto the obstruction bundle of Z. But if Z is a manifold, then the obstruction bundle of Z is 0 anyway. So that's why this thing happens. So let me just run through a few nice properties of D-manifolds. Try and persuade you that this is a well-behaved category of geometric objects. Firstly, in replying to Richard's question, a one morphism F going from X into Y in D-manifolds is an equivalence. In any two category, by definition, an equivalence is one morphism such that there exists a quasi-inverse G going from Y into X, and two morphisms, eta going from G of F into the identity on X, and zeta going from F of G into the identity on Y. So here's a theorem which allows you to glue two D-manifolds by an equivalence of open subsets. So if X and Y are D-manifolds, and U and V are non-empty open D submanifolds, and F is an equivalence from U into V. So our D-manifolds are required to be Hausdorff as topological spaces, so we have to impose this condition that the glued topological space, Z, which is X, union Y, where we identify points in U and points in V under their images in F. So if the glued topological space is Hausdorff, then there exists a D-manifold Z, which is unique up to equivalence in the two category D-manifolds. Open D submanifolds X hat and Y hat in Z, such that Z is the union of both. an equivalence is G from x into x hat and H from x into y hat, such that G restricted to U is 2 isomorphic to H compares with F. So a kind of obvious thing one would hope, which is that you can glue things by equivalences on open subspaces. It's important that we have partitions of unity in order to construct these equivalences. So, in fact, this thing can be expressed as a push-out in the two-category D-manifolds. So this is basically telling you that push-outs by equivalences tend to exist, at least provided the glued topological space is Hausdorff. Okay, so you can generalize this theorem to gluing families of D-manifolds, a very large family of D-manifolds, by equivalences on double overlaps, xi intersect xj, with conditions, compatibility conditions on triple overlaps, xi intersect j, xj intersect xk. In fact, these conditions are rather weak. On triple overlaps, you require only that some suitable two-morphism exists between the gluing maps. You don't require the two-morphisms themselves to satisfy any further conditions. So actually this gluing theorem makes sense in the homotopy category of D-manifolds, the homotopy 1 category. So this is very useful for proving the existence of D-manifold structures on moduli spaces, because at least in differential geometry, your moduli space tends to be, you describe it in terms of local coordination neighborhoods, and then this kind of theorem with many things you're gluing together will tell you that you can build a D-manifold out of all of these local coordination neighborhoods. Next, it seems to be a kind of general thing that you can lift one category notions in ordinary differential geometry up to two category notions in these D-manifold things. So let me tell you how vector bundles work out in this context. So vector bundles and cotangent bundles have nice two-category generalizations. So if X is a C-infinity scheme, you can define a two-category of virtual quasi-coherent sheaves, which are just morphisms in ordinary quasi-coherent sheaves. So a virtual quasi-coherent sheaf is a pair of quasi-coherent sheaves, E1, E2, and a morphism between them. When we think about E2 as being a kind of tangent space and E1 as a struction space or something like that. So the one morphism between these things are just commutative squares, and the two morphisms is a okay, so we've got E1 into E2. One morphisms one morphisms are columns like that. Two morphisms is a map like that for two one morphisms. So it just behaves as the obvious kind of two category of two-step complexes. Then we define something to be a virtual vector bundle if you can cover X by open sets U such that phi restricted to U is equivalent in the two category of quasi-coherent sheaves on U to something where the two sheaves are vector bundles, and the difference in the ranks is k. So if we write v vector of x for the full subcategory of virtual vector bundles in here, so then every D-manifold has a natural virtual cotangent bundle, T star of x, whose rank is the virtual dimension of x. And if you're given a one morphism in D-manifolds, then you get a natural one morphism, which is basically kind of df going between the cotangent bundles in the way you'd expect. But it turns out that your one morphism is étale, that is an equivalence on open, locally an equivalence, if and only if this morphism omega f is an equivalence of virtual vector bundles. So that's okay. So a smooth map of manifolds is étale if and only if it induces an isomorphism on cotangent bundles, and this is a derived version of this. So that is not true for schemes, for instance. You can find examples of schemes where the you get an isomorphism on cotangent bundles, but the morphism itself is not atiled. So you can characterize immersions or submersions by this morphism on virtual vector bundles being injective or surjective in a super sense. For virtual vector bundles, you can define a line bundle on X, which is in some sense the top exterior power of this virtual vector bundle. And then we can define orientations to be orientations on the line bundle associated with the cotangent bundle of X. So then you get the properties you'd expect from a manifold case, and from an oriented D-manifold, you can define a compact oriented D-manifold. You can define a virtual cycle, and which is what we're after. Okay, so I think I'll stop there. Thank you.
Questions? So what happens if you run this machinery for schemes instead of differential geometry? You're saying you get a known theory, you get a true truncation of a known theory.
I guess a two truncation of it. I haven't worked it out. Perhaps somebody's got a spare graduate student who could do that. But
You were saying, you were fighting with the fact that these are not schemes. Shouldn't it be much easier then?
probably it is, yes. But I don't want to get too close to Jacob Lurie. I'll fight with him, he'll win. Well, so there are advantages in this world. So the existence of partitions of unity is actually very useful. If we're going to do algebraic geometry rather than differential geometry, there'll be some other problems to solve, which I haven't attempted to solve. But my guess is that there should be a good algebraic version of this theory. And I don't know what it would do.
This
Yeah?
basic notion of the C infinity ring, I mean, isn't that essentially how Jacob Lurie even defines his infinity category of simplicial rings? He takes like the infinity space from, like, that includes all maps between just finite polynomial rings, and then he's like, that's the category of simplicial rings. So in a way, that's this question, right? This is even how he builds his idea in the structured ring topos or something like that. Just very obscure, but.
So far as I know, the derived algebraic geometry stuff doesn't involve C infinity rings. But David Spivak uses a simplicial version of C infinity rings to build his category. So there is some C infinity version of this. There is some simplicial C infinity version.
Isn't there a converse to your statement that they've been wasting their time, and it could possibly be that there's maybe some more structure that we're missing?
Oh yes. I was just trying to be provocative, really. But so I don't know how much structure this two truncation of mine forgets, or how important that is, and I'm hoping somebody maybe will tell me. Yeah?
What about fiber products in derived spaces? Do they respect weak equivalences? So if I want to take a fiber product of a diagram and I replace everything in this diagram by something weakly equivalent, will the fiber products be weakly equivalent?
What's a weak equivalence?
Oh, a weak equivalence in your category of an equivalence in this category of derived spaces. I take a diagram.
Yeah.
And now I replace everything in this diagram by something equivalent.
Yes. Well, these fiber products, they're two category fiber products defined by universal property. And yes, so replacing objects by equivalent objects, replacing one morphisms by two isomorphic one morphisms, doesn't change the fiber product up for equivalence.